Hi, everyone. How's it going? I hope you're enjoying yourself, and thanks so much for having me. Let's get started. So today I'm going to talk to you about sharded consensus, basically an approach to scalability known as sharding, but applied to consensus protocols. So here's the little outline of my talk. I'm going to try to get through it in about 20 minutes. So we're going to give you a little primer on consensus protocols and sharding, basically just the minimum that's required to give the rest of my talk. Then I'm going to talk about sharded consensus protocols kind of in theory, abstractly, and then I'm going to give a couple of more concrete examples of sharded consensus protocols that we've kind of worked on in CBC Casper research. And then I'm going to talk a little bit about things I didn't talk about, and then I'm going to conclude. So let's get started. What are consensus protocols? Well, they're kind of all about making decisions in a distributed system in a way that's consistent. And this in the context of all the things that can happen in distributed systems, like faults of various kinds. Normally we talk about safety and liveness, the idea that these nodes that are kind of somehow running these distributed systems don't make inconsistent decisions, and they eventually do make decisions. And there's some other things we want that I'm just not going to cover here for the sake of time. So consensus protocols decide usually either on, well, they decide on values, we're going to call it consensus values, or on predicates of values. So rather than deciding on the whole value, say, okay, the value has this property. And a binary consensus protocol, we're going to decide on a bit, 0 or 1. In the blockchain consensus protocol, instead, you decide that like some block is in the chain. You don't ever decide on a blockchain because it can always grow, but you decide this block is in the chain. And usually decisions are taken to be somehow output by the consensus protocol or committed to by the nodes in the protocol. So, a decision on a value is consistent with a decision on a value if they're on the same value. In this case, give an example of like 3-string 110 being consistent with a decision on the 3-string 110. Predicates are consistent if there's a value that satisfies all of them. So a decision that says the 3-string starts with 1 and a decision that says the 3-string starts with 0 are consistent because there's a string, for example, 110, that satisfies both. So the question I'm answering here is like, what does it mean for decisions to be consistent? And this means something slightly different in the context of deciding on values than deciding on predicates of values. And we're going to see that this is important in sharding because we're not going to be able to decide on the whole value because it's too big. We're just going to decide on predicates of values, which will let us say things about parts of the value. So some of this was really to say that consensus protocols are about making decisions about a predefined domain of consensus values. So different consensus protocols have a different notion of what it's deciding on, and consensus protocols are about making decisions on this domain of consensus values, be it by deciding on values directly or by deciding on predicates of values. Great. So hopefully that's super clear and relatively completely uncontroversial. Now we're going to talk about sharding. And here we have a sharded glass. It's very, very appropriate. So sharding is all about splitting up the work of a distributed system in order to scale its capacity. So really, fundamentally, the idea is we're going to try to scale distributed systems, scale their capacity, whatever that means, by splitting them up, whatever that means. Sharding, kind of got this from Wikipedia, was either coined by the Computer Corporation of America or by through this video game Ultima Online. It's about they used it really to mean using more computers as part of the system in order to either replicate or distribute the load. But fundamentally, kind of, if something's sharded, what we really mean is like it has more than one part. Fundamentally, sharding means there's more than one. It's like a bit is not sharded. This is kind of a really true thing. I hope you'll believe me. That a bit can't be sharded. There's no way to shard a single bit. And that kind of means that a binary consensus protocol is not sharded. There's no way to have a binary consensus protocol, a protocol that decides on a bit that is sharded. And that's going to provide us a nice little window. It's talking about sharded consensus protocols. Because at least we know something that, we know a consensus protocol that can't be sharded. Because any consensus protocol that's defined on the domain of consensus values bit can't possibly be sharded. Because sharding really means that there's more than one thing that we're deciding on at the end of the day. So we can't have a sharded binary consensus protocol. So what we really need is a sharded consensus value. So having a sharded consensus value is a prerequisite to having a sharded consensus protocol. You really need to have a notion that your consensus value has multiple parts. Fundamental. So remember, decisions are either on consensus values or the predicates. But because we want to increase the throughput of the protocol, we're going to insist that we're deciding on predicates rather than on the whole value. Because if we decide on the whole value, then nodes would have to decide on something for every shard. And instead, what we're going to do is imagine that nodes are interested in predicates that describe the value on some shards. So we're kind of imagining that nodes are not interested in the whole consensus value, but only some of it, which is possible because we're imagining that the consensus value has more than one part. Hopefully that all seems very straightforward. And somehow we have to have a notion of consistency of decisions, and it's like the same one as before. We haven't changed it at all. Basically, these predicates are considered consistent if there's a value in the domain of consensus values that satisfies all of them. So if you decide that like this sharded piece of the glass is a teacup, and I decide that like, you know, this other piece is from a wine glass, those like are inconsistent decisions because there's no, you know, liquid holder thing that satisfies both. So, you know, in consensus protocols, we have the opportunity to make inconsistent decisions. And in a sharded protocol, we have the opportunity to make inconsistent decisions about different parts of the system, about different parts of the consensus value, about, you know, different shards. So we got to choose different shards, things that are consistent for it to be a safe consensus protocol. So consensus protocols that are sharded require sharded consensus values. And the clients are interested in predicates of those values that only describe certain shards in some sense. So I'm going to give you piggyback off of your hopefully prior knowledge and tell you that sharding clients are light clients. You've maybe heard about light clients before. And they're a kind of consensus protocol node that somehow needs to do less work than like a full node. We kind of need to imagine, if we're going to have scalability, that nodes will only do work that pertains to certain decisions. Like if they're only interested in some decisions, then somehow they should only have to do some of the work. Otherwise, we're not going to get any scalability. We need to imagine that nodes working on one shard don't need to hear everything about every other shard. Otherwise, we're not going to have any scalability. So we're going to imagine that sharding clients are light clients. And it's going to turn out that this is like, you know, a perfectly appropriate decision. There's two kinds of light clients. There's light clients that don't look at all of the consensus value, and there's light clients that don't look at all protocol messages. And this is kind of a super interesting thing, so let me go into it. So we kind of are used to this kind of light client, or what I call a consensus value light client, where instead of the consensus value being the whole blockchain, you have a header chain instead. I seem to have lost this slide. Oh, here we go. This is the slide. I've just reordered them. So consensus value light clients, they're really about using the commitments of proof systems as consensus values so that clients don't need to know or don't need to ask about the full consensus value when they're asking about predicates of the consensus values. They look at like a Merkle root, for example, and they ask about properties of this Merkle root, which they can do through a crypto proof system. So consensus value light clients really are about, instead of putting the whole consensus value in the consensus protocol message, instead, you just use a Merkle proof or some kind of commitment to some kind of proof system that lets you prove things about the consensus value. So rather than the client having to have access to the whole consensus value, it can receive proofs, basically like witness data that shows them things about different parts of the full consensus value. So, you know, the blockchain header chain is an example of this kind of light client that basically minimizes the consensus value from including all these transactions and all this stuff that's in the blockchain to just Merkle proofs, Merkle commitments that can be used by light clients who are only interested in some part of the consensus value. So by kind of partitioning up the consensus value and using proof systems, clients can have access to and the ability to look at less of the consensus value. The blockchain header chain is an example, but also any sharding solution where you have something of the sort that you have like headers for every shard in the same chain, like a single consensus protocol, but the different headers affect changes or correspond to blocks that affect changes on different shards. This is like a kind of consensus value like client-only approach to sharding. There is, though, another kind of light client, which I call protocol message light clients. These clients only receive certain protocol messages. They have some kind of filter on messages, and they only receive the ones that are relevant to their decisions. Maybe they only receive messages from certain shards, for example. So if you think about like the world of blockchains today as a big sharded system, then like the fact that you only download Doge blocks when you're interested in Dogecoin corresponds to this kind of protocol message like clientness. Instead of downloading all the messages from all the chains, I only download the ones that I'm interested in. Also, sharding solutions where different validator sets are responsible for consensus on different shards tend to have this property where you can only download messages from certain validator sets because you're only interested in decisions on those shards. So there's two kinds of light clients, these consensus value light clients, which look at less of the consensus value using proof systems. And then there's this other kind of light client called the protocol message light client, which doesn't need to look at as many protocol messages. So there's two ways that we save, by not looking at all the consensus values and by not looking at all the messages. So now I'm going to move to this kind of more example, a little less theoretical, a little more concrete part of the talk, where I'm going to talk about like how we do this, actually come up with these sharded consensus protocols. Well, we start off by defining the consensus values. We have like a blockchain on every shard. And we have like, shard IDs to identify the shards, and then I define like sent and received message queues for every pair of shards or certain pairs of shards, that keep track of the messages that were sent and the messages that were received from different shards, among some other things. Here's like a little code snippet from our the CBC Casper GitHub and our ETH sharding POC. We have a bunch of different things that are in a block, including the shard ID, a previous block, the transaction log, the sent log, the received log, sources, which are like things from, like the blocks from other shards that we're receiving messages from, virtual machine states, all sorts of stuff that is like part of the data structure of a block. So we define first we define the domain of consensus values that the protocol is interested in, and that nodes are going to make decisions about. And then we define a fork choice rule, which governs kind of which validators have control over the state of the consensus on which shards, and which makes sure somehow that the communication between the shards is consistent, or so that like the decisions that nodes make on different shards are consistent with each other. So like if we allow the chains on every shard to be completely independent, then there wouldn't be that much of a notion of cross-shard consistency. But instead, if we insist that, like, for example, a message that is sent should be received, and we shouldn't have like a finalized sent message that is finalized not received, which is like a kind of atomicity constraint, then, or as soon as you have any kind of constraint about the state that different shards should be on, then the fork choice, this kind of estimator, this thing that relates protocol states to consensus values, is going to have to do some work. And I'll describe that a little more when I get into an example. But so let me just take a step back. So the first thing we do is we define the sharded consensus values, and then we define this fork choice rule, which kind of from a set of protocol messages will give you a fork for every shard in this very blockchain-esque kind of way. And this is something that if you've read and already know about the CBC Casper framework, like you'll understand, because the estimator is like one of the main parameters of the CBC Casper family. So I'm going to show you some examples and kind of walk through what's happening here. So we have, in this case, a sharded consensus protocol with two shards corresponding with two blockchains, one in the parent shard and one in the child shard. Each of these each of these horizontal lines are identify messages sent from the same validators, and these red dots are messages that are sent across shard. And the fork choice rule of the parent is kind of completely independent, whereas the fork choice rule in the child orphans blocks that don't synchronize with the parent appropriately to make sure that all the messages are received once in order in the fork choice. So the kind of work here was first defining the block structure, which includes the shard ID and these messages, and then define a fork choice rule, which will pick out chains of this consensus protocol, chains of blocks from the blockchains produced by these nodes, in order to maintain this cross-shard consistency property. Here's something a little more sophisticated. In this kind of sharded consensus protocol, we have a notion in the consensus value of which shard is in the parent position, and a way for that to change over time. So this basically corresponds to consensus values that are a little more complicated because they allow for the shards to be in different positions, but still the work is the same. We define the consensus protocols and then we define the fork choice rule. In this case, the fork choice rule understands that some blocks, these purple ones, are root blocks, and these teal ones, or these beige ones, are child blocks, and they have like different properties in the fork choice. This sharding solution demonstrates, this animation of the sharding solution demonstrates message routing, which again is just done with the fork choice rule and the consensus values by defining, the sent messages and adding a destination to each message and using a routing table to say where the messages have to be forwarded. So at the end of the day, the cool thing about the CBC Casper approach is that we can define rather complicated consensus protocols and fork choice rules without having to think again and again about the foundations of the consensus protocol stuff, because it's all inherited from this framework for making decisions in consensus protocols that the CBC Casper stuff offers. So in this protocol, a node that's following shard 3 doesn't need to know about everything that happens on shards 2 to 6. Like 2, 5, and 6, because the fork choice rule on the shard 3 doesn't depend on the fork choice rule on those other shards. And so they won't need to receive all the messages from these other shards, and we'll get some scalability via not receiving all the messages, which is this second sense of light client, that you're not receiving all the messages, but you're only receiving the protocol messages that are relevant to the decisions that you're making. So in future work, we have to define one of these are two of the kind of main pieces of work that are left to get the CBC Casper sharding solution to a point where I feel super happy. We don't want to have like a consensus values and fork choice rule that will let us have consensus on a non-deadlocking execution of the Ethereum virtual machine. So one of the issues, if you allow the Ethereum virtual machine to do cross-shard calls with synchronous calls, is that you can get into deadlocks, where a contract is waiting for a return value, and another contract calls it, and then it waits, and then you can get this cycle where everyone is waiting on each other. So if we have a consensus value and fork choice rule for that will be basically the blockchains that record execution of the virtual machine that is deadlock free, that would be super cool. I have real reason to believe that it's possible. And this will allow basically synchronous calls in the virtual machine across shard. And another thing that we really need is the load balancer, so that the load on the different shards will be balanced over time, so that you can't, for example, overload one shard and make it prohibitively expensive to participate or use that shard. Load balancing also reduces the overhead of the routing protocol, and so we get a lot of scalability from load balancing. So if you're interested in these relatively tough problems, do contact. So I have a bunch of discussions that have been completely omitted from this conversation. So you might ask me, what about liveness? Well, liveness isn't really in scope right now because it's something that we're going to work on for consensus protocols, and for sharded consensus protocols, it's actually a very similar kind of solution will apply. If you like the liveness strategies for individual shards for a single blockchain, we'll also work on these shard chains. Non-triviality, well, I would love to talk about it, but there's no time. Validity and data availability are problems that we often talk about in the relation to sharding, but which I usually omit or delay for later because I regard them as not consensus protocol problems. Like consensus protocols are about making decisions in distributed systems in the context of mutually exclusive possibilities, but validity and availability aren't consensus protocol problems. There are other kinds of distributed systems problems, and the kind of problems that I think we can definitely solve once we have scalable consensus protocols. Validator rotation, what I've loved to talk about, didn't really have time. Proof of stake and crypto economics. Also, you would maybe expect some of this from me right now, but since these systems are designed to be incentivized, we can kind of leave those conversations for later. And also, this talk is really just a distributed systems talk. So let me kind of wrap up by going over the main takeaways. So some things I hope you'll remember. Binary consensus protocols are not sharded. They cannot be sharded. Sharding consensus requires sharded consensus values. Sharding clients in a sharded consensus protocol are light clients. Sharded consensus protocols exist and are possible. There's actually a huge family of sharded consensus protocols. And sharding is a natural way to scale consensus protocols, especially if you're talking about consensus protocols that replicate something like a virtual machine or something that naturally has different components. So I hope that this is convincing. I hope that you're convinced. And thank you for listening. Thanks for having me. Please reach out and contribute to this work.
Okay. Thank you very much, Vlad. And we will, again, defer the questions for later, have a joint Q&A. And now, please welcome Vitalik, who needs no introduction. But yeah, thank you very much.